want to try a problem I missed yesterday? Where's my... Hang on 2 seconds. Alright. So we shall try this problem. 2615, sum of distances. You are given a zero-indexed integer array, nums. There exists an array of length nums, okay, where array at I is the sum of the absolute value of I minus j over all j, such that nums of j equals nums of I, okay, and j is not equal to I. So taking all the positions where you have the same number, getting those distances centered around the particular position I, adding them together and making array at I equal that sum distance. If no such j exists, then array at I is equal to 0 and return that array. So yeah, let me just check this. So this is 2615, sum of distances. Fine. And so for example, if you have nums 13112, you would expect, so the indices are like 0, 1, 2, 3, 4. The output array would look like, so if I focus on index, so it'll be the same length, 0, 1, 2, 3, 4. If I focus on index 0, I'm looking for all the places that also have a 1, it's here and here. I get those distances, so 2 and 3, so the sum of that is 5. If I look at index 1, I'm looking for all the 3's. There are no other 3's, so this should just be 0, I think. Looking at index 2, I'm looking for all the other 1's, which are here and here, so the distances are 2 plus 1 gives me 3. And then looking at index 3, I'm looking for all the 1's, which are here and here, so I've got 1 plus 3 gives me 4. And then looking at index 4, I have a 2. There aren't any other 2's, so I think this would be my array. It's my understanding of the problem. 5, 3, 33, 4, 0. Yeah, okay. So that's how that works. And then in the second example, it's all zeros because there's no duplicates. So you're looking, okay. Constraints 10 to the 5, so looking for something relatively linear, maybe n log n in the worst case, that kind of thing. No n squared though, that's for sure. Okay. Well, my first instinct is like build hash table, where your keys are your are your unique elements, so 1, 3, and 2, and they map to a list of positions, so 0, 2, 3, index 1 by itself, index 4 by itself, and the idea is, maybe this isn't so helpful actually. For each index, I find what the number is, and then from that number, I'm able to find all the positions that have the same element. So if I look at a particular position and I see it's a 3, and I look up 3 and I see there's only one index, then I know that there has to be a 0 in the array because there's no other elements to do this distance thing with. So yeah, if the length of ht at a particular key is equal to 1, then the array at ht k0, I guess, like accessing that particular position, should equal 0 kind of thing. This is just a way of like easily handling the zero case, but it looks a bit convoluted. Anyway, now the more interesting case is when you do have duplicates, like in this case. If I focus on index 0, sorry, for example, I look up the fact that there's an index of 1. An element of 1, so I know I have to look in here, and I see that, okay, there's a 1 at index 0, there's a 1 at index 2, and there's a 1 at index 3. That's what this information is telling me. So what does that tell me? How do I process this array so I can easily find the sum here and here? So let me try and like separate this out. So we have a 1 at index 0, we have a 1 at index 0, a 1 at index 2, and a 1 at index 3. Index 0, index 2, and index 3. And you know that's what this information tells us. From there, how can I pre-process these sums at all? So for example, if I know that the distance between the first two guys is 2 and the distance here is 1, just by looking at adjacent pairs, can I quickly compute things or no? For example, I know that the distance between you and you is 2, and I know the distance between you and you is 3. I'm just concerned about how to do this quickly, because I feel like I don't really know how to do this efficiently. 2, then 3. So like, okay, that gives me 5, so array at index 0 should give me 5. Fine. But that kind of took linear time, I feel. We'll see. And then let's say we have, if we focus on on index 2 now, this is the 2 and this is the 1, so you get 3. Okay, to get from index 0 to index 3, you could say we have to do this and this. This distance plus this distance. So maybe, how do I really quickly figure out the sum for this guy? How do I organize the positions? Index 0, in a sort of linear fashion, I'm able to figure out the distance between two adjacent ones. Or even, maybe it's better to find the distance between the first one and each subsequent one. That is, from here to here, it's 2, and then from here to here, it's 3. Then the sum of these two gives me the first value. And then if I focus on this guy, it's basically the same thing, except I don't have to do the full 3. I just have to do a 1. So it's like 3 minus 2 or something. And then plus the 2 to get back over here. This is so strange. And then if I look at index 3, I just don't see how this generalizes. 3, there's no more things ahead. There's no more ones ahead of the index 3. So, bless you. There's no things ahead of this index, so I have to only consider the ones behind me. 1 plus 3. But I can't look up those numbers one at a time because I feel like it'll get too slow. I can do this like with a sort of brute force-ish method, but I just feel like it's going to be way too slow. So how do I do this in more linearish time? 0 to 2 to 3. Alright, let's maybe we'll start with the sort of more n squared solution, see what if we can find any redundancies. What I would do is I would probably do with the initial strategy. I would say, let's find the gaps. Let's find the size of the gaps. So between here and here is 2, and between here and here is 1. So then array at 0, I know is equal to the first gap plus the first gap and the second gap to get like that and to get to that, you know? So it's like, it's 2 plus 2 plus 1 gives me 5. Array at index 1, sorry, at index 2, this guy, is it's this gap plus this gap. So 2 plus 1 gives me 3. Array at index 3 is this gap plus this gap and this gap. Ignoring this dot. It's this gap plus this gap and this gap. So it's 1 plus 1 plus 2 gives me 4. So specifically, from the 0 to 3 list, which came from over here, what would I do? Create 2, 1, the difference between these two and then the difference between these two, to make 2, 1. Then focusing on the leftmost position, I know that the sum is 1 of these plus 1 more and 1 of these, and if they were multiple, I would do plus 1 of these, 1 of these, and 1 of these. That didn't make any sense. Oh, sorry. Maybe this isn't so helpful. Maybe there's a better way. I guess, yeah, if it does feel kind of n squared, I guess we could just iterate through. For each index, we could iterate through again. Hang on. Let me think about my time complexity. Let's say, suppose di refers to the number of times element I exists in the array or whatever, in the thing, in nums. And suppose there are k different or distinct elements in nums, right? So, i.e., the total number of elements is equal to d1, or d alpha 1 plus d alpha 2 plus dot dot plus d alpha k, where each alpha refers to the particular element and d refers to how many times they appear. So figuring out the sum, figuring out the distance value for a particular unique element and for all of its instances, I think would take O of d I squared. And I have to do that for k elements. So So total time complexity, I think, is O of k times O of d I squared. Or rather, it's O of d alpha 1 squared plus O of d alpha 2 squared, O of d alpha k squared. So I have to do that k times no, so it's like, yeah, it's roughly n squared, right, if I do it like this. So yeah, I think it's too slow. Sorry, that was a big thing for nothing. I just thought maybe I was just meant to brute force it, but I don't think I am. I'll just move it to the side. Oh, there must be some kind of math trick or something that I can do, because like I have the positions for a particular element. I have 0, 2, 3. Surely I can sort of process those numbers so that without explicitly finding every individual distance. Surely I can. All right, let's say we have more than 3. I think 3 elements is too small. Let's say we have, let's say it's element 1, but it's at position 0, 2, 3, and then like 7, 9, 12. These are my indices. In fact, I'll make them green because I normally do indices in green. Right? Like, let's say those are my positions. So my array at index 0 should equal 2 plus 3 plus 7 plus 9 plus 12. Plus 7 plus 9 plus 12, which gives me 5, 12, 24, 34, 33. Right? 5, 12, 24, 34 minus 1 gives 33, yeah. Okay, so you have like that value. So let's say we brute force that, we just figure out all the other elements. That took sort of O of di time, right? Going through all the iteration, all the instances. But then from there, is there a way that I can kind of do like a constant time type thing? Array index 2 is like, if I just focus on the forwards, it's like this, 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 and this. Which is kind of similar to, it's just I don't have to cross this border. I don't have to cross this as much, I think. So like, this is of course a jump of 1, and this is a jump of 4. But this was a jump of 3. So this jump could be considered as like 3 minus the 2. You know? So this 3 could become 3 minus 2. This 7 could become 7 minus 2. Plus 9 minus 2. Plus 12 minus 2. You know? But there's plus this guy. Plus the 2 on the end. Which I'll do in red. So the blue is like the stuff in front of you, and the red is the stuff behind you. So you got 1 plus 5 plus 7 plus 10. Is that accurate? So 1 plus 5 plus 7, yeah, that is. Plus 2. Plus 2 because of going backwards. Right? So you get 17, 22, 23, 25. And so just considering that, this is 3 minus 2, 7 minus 2, 9 minus 2, 12 minus 2. And there's also a 2 as well. So I don't know if this is helpful, but you could write it as, I'm not sure if it's good to, you can kind of write it as like array 0, because that's the 3, 7, 9, 12, and the 2. 3, 7, 9, 3, 7, 9, 12, and the 2. Minus 2, minus 2, minus 2, minus 2. So it's array at 0 minus 4 lots of 2, because you had 1, 2, 3, 4 things to jump to ahead of you. So that's the same as sort of going 1, 2, 3, 4, but without having to do this extra jump of 2. So you had to subtract 2 off each time. So 4 is like how many numbers are ahead, which should be pretty easy to find, because I would know the length of this list, and I would know what index I'm up to. Interesting. So array 0 minus that. If I try to do that for, and does that work? So it would be 33 minus 8, which does give 25. Okay, so that math-wise that works out. And then if I focus on index, if I focus over here, it's this plus this plus this. Can I apply a similar trick? What would I do? Is it the same as like this plus this minus the 1? Maybe. So yeah, array at index 3, this 3 over here, would be what? This jump can be the same as this jump minus 1. But I didn't really, did I? I kind of did this jump. This jump plus this jump plus this jump. This jump plus this jump. This jump, this jump, this jump minus 1. It's 4, 6, and 9. 4, 6, and 9. Those are my jumps. Let me get rid of all my squiggles. It's getting a bit cluttered. Let me just try something real quick. I don't know if the mic is picking that up. There's like a weird pulsing sound happening. It's kind of quiet though. I don't think it'll be that noticeable. Array 2, just for clarity, is 2. That's the backwards 2. Plus, and then 1 plus 1 plus 5 plus 7 plus 10, right? Those are the forward jumps. Array 3 would be what? Let's not worry about the forward stuff too much. The backward stuff, I mean. So it would be 4 plus 6 plus 9. That's the forward jumps. Plus some red stuff. It would be plus 1 plus 3, right? 1 and 3. Now the 4, 6, and 9 stuff in particular could be written as 5 minus 1, this jump minus this jump minus this, so 5 minus 1 plus 7 minus 1 plus 10 minus 1. Notice how we got 5, 7, 10, 5, 7, 10. We got minus 1, minus 1, minus 1, 3 minus 1s because there's 3 numbers ahead, so that pattern kind of continues. How do I deal with the red numbers? I've got a plus 1, which kind of tracks with the plus 1 over here, but I've also got a plus 3, which is like the plus 2, but with an extra 1. Yes, because it's the same as doing this jump, but it had to first go to 2 before it did this final bit. Like this red, no, I should do it in red, sorry. This 3 over here, can be thought of as this 2, which is this guy, plus an extra 1, which is why we get 3. Okay. So the red numbers, okay, let's just write it out. So it would be 5, 7, 10 plus 1 plus 2 plus 1. So you got 5, 7, 10, 1 and 2, 5, 7, 10, 1 and 2, and plus an extra 1. So you have the array of 2 minus 3 times 1, where 1, so 3 is, 3 is how many numbers are ahead, and 1 refers to the gap between 3 and the previous number, and then plus an extra 1. This guy wasn't accounted for by array 2. So it's very similar. This had like a plus 0 on the end maybe. This had a plus 1 on the end. Let's do another one. I think we're on the right track. If we focus on array at 7, there is some kind of pattern emerging. It's just kind of involved. Array at 7 can be written as 2 plus 5. And then the red numbers would be 4, 5, and 7. So using those similar ideas, it can be written as 6 minus 4 plus 9 minus 4. Right, 2 and 5 become that. Plus the 4 the 5, and the 7. So array 3 is like 4, 6, and 9. We've got the 4, 6, and 9. The 5 and the 7. Damn, these backward numbers make it really hard. Minus 4 times 2, or 2 times 4, because there's 2 numbers ahead. So that pattern holds. The 6 and the 9 show up as expected. The 4 shows up as well. That kind of happened last time as well, where one of the red numbers showed up. Right, like the 1 showed up. What is left? 4, 6, and 9. You have a 5, a 7 versus a 1 and a 3. So you're supposed to have another 4, you have another 12, so it's like the carryover becomes like 8. Can I understand where that carry came from? If I can figure that out, I think I'm pretty much there. 6 minus 4 plus 9 minus 4. I don't know why I put so many brackets like that. Plus, instead of 4 plus 4, plus 4 actually, sorry, 4 is good. And then we have 1 plus 3 plus 8. So 4, 1, 3, 9, and 6. 4, 6, 9, 1, and 3. All those numbers are there. 4, 6, 9, 1, and 3. And there's an 8 left over. So this would be array at 3. 2 times 4 plus an 8. So we had a plus a 0 then we had +1, and then we had +8. Okay, so if I can figure out where that numbers comes from, because I'm just numerically crunching right now. I'm not actually understanding what's happening. If I have, okay, in the very first instance, there's no real numbers behind us. So this we did by brute force, and in this instant, this one has like kind of the same jumps. This was like bang bang. Whoops, I'm overzealously drawing. Bang 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 and bang. This had sort of the same jumps, but I subtract off this plus this, and this backwards jump is the same as this forwards jump. So there was no real like excessive bits to throw on. I guess there was nothing really excessive to put. So I guess we put a +0. But for array 3, forward jumps like we observed are like the same as these jumps, but we subtract off the 1 each time, so we can count for that. And then this backwards jump is the same as this forwards jump from array 2. So the array 2 had this forwards jump over here, so the backward jump over here also kind of, the backwards jump makes sense. So this backwards jump is kind of the same as this backwards jump. Oh, wait a minute. I think I get it. The excess number is how many numbers are before you times the difference between, or something. Wait. My brain just like smacked itself. Okay. Wait. I think I'm almost cracked it. So the same numbers ahead, and then this backwards number is the same. The backwards number here is the same as the forwards number from array 2, which is why array 2 had a 1, and the backwards number here is the same. Now, the backwards jump here, the backwards jump to apply over here is the same as the backwards jump over here plus an extra 1. Which is why we get a 2, because it's that backwards jump plus a 1. Okay, I think if I do one more, I think it'll make sense. So, looking at index 7, these forwards jumps are the same as these forwards jumps, but minusing off the 4 each time. That's why we have the -2 dots of 4. This backwards jump is the same as this forwards jump, which is why the 4 over here matches the 4 over here. The backwards jump over here matches the backwards jump over here plus an extra 4. That's why we have 1 4. That's why out of this 8 there's 1 4. And then, oh my god, it makes sense. And then this backwards jump is the same as this backwards jump plus another 4. So it's the exact same jumps, but you have to add 4 and 4 again, which is why you get 8. So the 8 should actually be written as 2 lots of 4. 2 because it's the question of how many number of numbers behind you -1, and 4 is the gap, is the jump between you and your previous number. Okay, this might make 0 sense. This refers to so the 4 is a gap between you and previous number. 2 is how many numbers are ahead of you. I think I've cracked it, but it it's crazy. It's not crazy, but it's, I don't know, it's a bit wacky. I get it though, but I don't know if it made any sense coming across on the film. I was recording, right? Okay, thank God. If I did all that and wasn't even filmed, that would be really sad. I think it makes sense. Okay, so in general, here's my plan. In general, for a particular element, call it K, K will map to a bunch of positions, sorted, I1, I2, up to ID, we'll call it, right? Where there's D instances of this particular element. The array at I1 will equal, and we will brute force answer, and then for I2, I3, up to ID, for each of these, for each I2, I3, up to ID, okay, array at that particular position is gonna equal, at I alpha is gonna equal array at I alpha minus 1. That's what's happening here. So it's not I minus 1. It's not like I'm specifically looking at, you know, from 7 I'm looking at 3 because that was the previous element in the list. Right? Before 7 there was a 3. This is getting really messy, but it makes sense. Plus or minus I alpha minus 1, that's the gap size, times how many elements are ahead. Number of elements ahead. So this is like referring to this part. And then we're adding the excess term, which is I alpha minus 1 times number of elements behind minus 1. Minus 1 because we care about, like, for the example of the 7, for the example with the 7, you know, this backwards jump, for example, is identical to this backwards jump, which is great. That just contributes to the array term without any fuss. However, this backwards jump, this backwards jump, if I'm trying to use the array 3 thing, it's the same as this backwards jump plus this guy. So when my perspective is on the 7, you know, this guy is no trouble, but these two are the ones that need to have an extra 4 added to them, because this backwards jump is this backwards jump plus the extra 4. So I need to care about this element and this element, which is, you know, how many elements are behind the 7 minus 1, because I don't care about that guy. Okay, so my formula, number of elements behind minus 1. And this is my formula. And I do that throughout the hash table, and I think I've got it. This is crazy, by the way. All right, let's try it out. So step 1, build the hash table. HT is equal to bin. For I and num in enumerate, oh, I should do default dict. From collections, import default dict equals default dict list, I think, ht at num dot append I. So that will build the hash table that we're kind of considering. And then we also want to make an array thing. We'll say 0 times the length of nums, so that will make an array of the same size. Then we can also index that thing without any issues. All right, here we go. For the distinct element k in ht, so for each distinct element, if the length of ht at k, if that particular list of positions is equal to 1, if there's only one thing, then continue. We've already set things to 0, so I shouldn't have to do anything. Now, otherwise, we will process the numbers using this formula. For I position in enumerate ht at k, if I equals to 0, then for position, no, for next position in htk from 1 onwards, array at the particular, from 1 onwards, the array at the particular position, this position of this particular element, needs to add on next position minus position. And that should basically brute force the very first element, as we did here. We're just getting all the jumps. That's all we're doing. Okay. Then from there, else, the gap we care about, right? Because the formula is like I alpha minus 1. So we care about the gap is equal to position minus ht at k at I minus 1, I think. Getting the value of the previous position and finding the difference between them. Because position will give you the 7, for example, and then this term will look at the same list, but we'll go back at an index. So you'll get the gap. So gap is referring to like the I alpha minus 1 here and the I alpha minus 1 thing here. Elements ahead. So for example, looking at my rough working, the indices, the I values will be 0, 1, 2, 3, 4, and 5, with a length being equal to 6. So if I'm at index 3, that means the number of elements ahead is the length minus my index minus 1. 5 minus 6, 6 minus 3, minus 1. Because it should be 5 minus 3 to get, yeah, that makes sense. So the length of ht at k, that particular list, minus my current index, and then minus 1. And the elements behind is equal to basically my index. Yeah, just my index, right? If I'm on index 3, that means there's 3 elements behind me. Okay, so there, and then using my formula, array at this particular position is equal to the array at the other position ht at k at I minus 1, so that's getting this value minus the gap times the elements ahead. Maybe num elements ahead is better. Plus the gap times the num elements behind minus 1. Oh no, the lines are getting too long. Oh. And then we simply return the array. It's like a weird like DP element almost, like I don't know, like because you're like using the previous thing kind of, but it's I guess it's more like a math trick more so than DP. But assuming this formula is correct, then I think I should be good. Just in terms of time complexity, what's happening is for k in HG, so that's the O of like, so yeah, sort of taking the same sort of time complexity logic. Suppose di refers to the number of instances or occurrences of element I in nums, right? Suppose there are k distinct elements in nums, therefore n, the length of nums, is equal to d alpha 1 plus d alpha 2 plus d alpha k. So applying that logic, we're going through each key, which is O of k, because there's k distinct keys, times, we're doing, for each of those, we have to do sort of one iteration. O of sort of the I, which is like, yeah, sort of like your O of n, because like the product of this and this, I guess strictly speaking, it's like O of d alpha 1 plus O of d alpha 2 plus O of d alpha 3 plus O of d alpha k, which is equal to O of n, because what I'm saying is this for loop will take O of d alpha I time, and I'm going to do that for each element, so we get a summer like that. Alright, let's see how this goes. Whoops. Oh yeah, of course. That was like the weird thing that happened. Do I just send it? It's kind of late, so... Yeah! Come on! It worked! The formula worked! It's not a strict proof, but I think the example was quite eye-opening enough that I think it made sense. Like, you would just have to sort of write it generically. Instead of putting strict numbers, you would have to put like an arbitrary number of random elements, sorted of course, because it's positions that are put in sorted order. And then you would have to just sort of say, you know, for the 0 case, for the I equals 0 case, then you know you brute force it, so of course it's correct. And then for every subsequent case, you'd have to sort of speak generically, sort of do an induction idea. You know, assume you have the correct distance for the previous element, and then like blah blah blah. It'd be hard to write though, because I feel like it was a lot easier when you had concrete numbers to work with. You could really see how the numbers work. I don't know how you would write a proof of that, but smart people could. Oh, I'll take it though. That wasn't easy. That was like, that required some like legit like math tricks as well. Is the topics math? No. Prefix sum? That sounds kind of crazy. Can we use prefix sum here? Apparently. The prefix sum array. Does that work? The indices to the right will be the regular subtraction, while the indices to the left will be the reverse subtraction. Wait, what? Okay. Indices to the right. Maybe I should read the, but it is late, so I'll allow it for now. We had the right idea, you know? I'm sure, I guess there are some more coding tricks type thing you could do. Yeah, this is all the same. For each key, total equals the sum of those positions. Interesting. I'm assuming this applies the same sort of principle, but does it in a better way than what I did. Well, I'll read in my own time. I'll read in my own time.